In this video, we'll discuss expected value. Now, the expected value represents the average financial outcome of an experiment over a long term, and we often use this with gambling as well as with different financial situations. The expected value is often written as capital E of capital X, and it represents the probability of winning times the amount that can be won, and we use that as P times S, and this is the most common way you see it written. Now, it is possible that the expected value can be made up of multiple expected values. So the overall expected value will equal the sum of the individual expected values in a situation. It's just going to represent the probability of the first event times its potential winning, plus the probability of the second event times its potential winning, and so on and so forth. Now, when we're calculating the expected value, we're going to use some shorthand to help us. If we see P, that's the probability of winning. Q is going to be the probability of losing. S will be the earnings from our winning. C will be the cost of playing, or the cost of participating. And L will be the losses from losing. And I'm going to use these letters to help us understand what's going on. So one of the ways that we can calculate is to look at the gross profit idea when there's a cost to play. When this happens, we're going to calculate the gross profit of each expected value, add them together, and then subtract the total cost to play. Another option is to look at the net profit of the expected values. To do this, we take the net profit of each individual expected value. So that means we're going to take how much can you win minus the cost to have participated or played. We're going to add all of them together, but we're also going to calculate the expected cost of losing. So we get that expected value. That's what we subtract in the end versus the total cost. That's the difference. Do we want to deal with the gross profit, or do we want to look at this from a net profit situation? They are equivalent formulas, just sometimes one can be easier to use than the other. Now there's a third method that will show up at times, and there's probably other ways that can be done, but these are the most common ways that we'll be dealing with it. And that is the cost to losing. When this happens, we're going to calculate the expected value of winning. Then we're going to calculate the expected value of losing, which would be that probability of losing times how much are you going to lose. And then what we do is we calculate the difference of those two values. And this often happens when we're looking at bidding for certain projects in financial situations. Let's look at some examples to help us out. So suppose a gambler plays a $20 game where they roll a single fair die. They'll win $30 if a 6 is thrown, or $60 if a 5 is thrown. How much would the gambler expect to win on average? Again, because they're playing this game a ton of times, and it's looking at the average amount won per game. Not what they're going to win on a single game, but over the long term, what are they winning on average? So if we look at the first method, that gross profit idea, we're going to calculate the expected value of winning on a 6, calculate the expected value of winning on a 5, and then subtract out the cost to play. So the probability of winning on a 6 would be 1/6 times $30, because you have a 1 out of 6 chance on a die to roll a 6. And when I multiply them, the expected value would be $5. So if that was the only thing, we'd say the expected value of winning with the 6 is $5. But we can also win on a 5. And this would be the probability of rolling that 5 times the $60 for winning. So a sixth of $60 is $10. But we also have to remember that we paid to play, and that cost was $20. So that means that the expected value overall will be the expected value of winning with a 6 plus the expected value of winning with a 5 minus the total cost to play the game, which would be $5 plus $10 minus the $20, or negative $5. This means that the gambler should expect on average to lose $5 each time they play. Now, think about what that means though. There's no way for them to win or lose exactly $5. But if they average out what they do over the long term of playing, they will lose on average $5 per game. Now, let's look at it from the net profit idea. So here, we're going to be taking the cost out of the earnings. So when we think about winning, it's not winning $30, it's winning 30 minus 20 because you had to pay to play. So really you're winning a net profit of $10. And that's 5/3 dollars. Yes, that's $1.67, but we want to make this as accurate as possible all the way to the end before we round. So use fractions and use your calculators to help you with that. Same thing when we look at winning with a 6. It's not winning $60, it's winning 60 minus the 20 that was needed to play. So really, it's winning $40. And that would simplify to 20/3. And again, keep the fractions, it will make it more accurate in the end. Now the distinction is, because we're calculating the net profits, we need to calculate the expected net loss. That would be the probability of rolling something else times the $20 it costs to play. So that could happen from a 1, a 2, a 3, or a 4. That's 4/6 times the $20, which is 40/3. And just like before, I'm going to combine these values. The expected values of winning minus the expected value of losing. And when I do this, 5/3 plus 20/3 minus 40/3, that gives me negative 15/3, which is negative $5. Now, if I use the rounded versions, I would end up probably something like $4.99 or $5.01. So it's going to be close, but it's not going to be accurate. That's why I want to maintain and keep the fractions until the very end. And then you can round it to the nearest penny. So whether I used method 1 or method 2, it still came out that the gambler would lose on average $5 each time they played. Now let's look at the situation of making bids and see how we can come up with this idea of how the third method works. A construction company is determining whether to put a bid on building a new store. The probability of winning the bid is 70%. If successful, they will earn $255,000. But if they lose the bid, they will lose $100,000 in revenue. How much should they expect to earn if they put in a bid? And this is where that third method can be very helpful. We can calculate the difference of the expected value of winning and the expected value of losing. Let's start with the expected value of winning. In this case, there's a 70% chance of winning, so that's 7/10, and if they win, it's $255,000. That would be a total expected winning of $178,500. Now we have to think about the expected value of losing, because no explicit percent is given. But think about it as a total percent. If it's 70% chance of winning, what's left? 30% chance of losing. So when we think about the expected value of losing, that probability of losing is 30%, or 3/10, times the $100,000 that would be lost in revenue, which is $30,000. So to calculate the overall expected value of earning, we're going to take the expected value of winning minus the expected value of losing, which would then give us $148,500. So the construction company, in this case, should expect a profit of $148,500 if they put in a bid on this new store.